somewhat dreary night. My name is Lily. I am a PhD student at Stewart Observatory, and I'm very happy to welcome you all here. So this is SpaceDrafts. We're part of an international network of Astronomy on Tap branches, which is organized by astronomers all over the world to teach the public about really cool astronomy. Yes. I did not know where I was going with that.
You did great!
Can you tell I have emceed like twice? So, as many of you probably know, we are next to a very active train track, so inevitably...
Oh boy. Okay.
Sorry, we're trying to figure this out. So inevitably at some point during this evening, there will be a train that comes by, and it will ring its horn, and we will not be able to hear the speaker. So, when that happens, if you happen to have a drink, we like to pick it up, toast the train, and say choo-choo. And if you don't have a drink, join in along in saying the choo-choo anyways. I am so sorry for all the technical difficulties.
It's not SpaceDrafts if we don't have technical disasters. Oh my gosh, it's worse.
I'm going to turn this off while we figure this out.
5-minute break! It's not SpaceDrafts if we don't have some kind of technical disaster, huh?
What the heck?
Well, there should be feedback in front of you. So I'm trying to keep it calm. Right? What if
I'm going to talk while Logan very slowly turns the volume up and hope we don't get feedback.
in the back?
Can people in the back hear? Good? Yeah. Okay, thank you. Thank you for your patience.
Well, here it is.
Thank you for your patience while we get this sorted out. So tonight we have a couple of new things. First of all, our merch table is back here, and we have new merch. So if that interests you at all, please come drop by and check it out during intermission and after the show. We will be back there. We can unfortunately only take cash, but if you're interested, we are happy to have you buy from us. And we also have a new segment, Astronomy in the News, which is going to be presented after intermission by Drs. Jackie Champagne and Danny Kolakowski. So stick around after intermission for that. And instead of a second talk tonight, we also have a really cool trivia event planned where there will be a $25 Borderlands gift card up for grabs. So if that interests you at all, please stick around after our first talk. So now without further ado, did I get all of the announcements?
I wasn't listening.
I think I got all the announcements.
Okay.
So, so without further ado, and now that we're not going to trick Brenda, I would like to introduce Dr. Brenda Fry. She's a professor at Stewart Observatory, and she will be telling us about a lot of new exciting science that we've been getting from the James Webb Space Telescope.
Thank you. So I wanted to say straight away that I hope to really, share some stories with you, and I'm really glad to be here to get to do that, and to be able to have the conversation goes both ways. Please let me know if you have questions at any point along the talk, because I want to let you come with me and not kind of like leave you behind. Okay? So if I talk too fast or would you repeat something, please raise your hand. Or you just want to get a different part of the story, then do that. Okay, so let's see if I can test. There we go. And testing. Okay.
Point at the laptop.
Huh?
Point at the laptop.
Point at the laptop. Oh.
PowerPoint also needs to be
Oh, that's my bad. My bad. My bad.
Okay,
Sorry.
More difficulties?
Try it again.
We're okay. We're okay.
We're okay now. All right.
You can stand back there.
We can
but-
stand back. Okay.
Yeah.
Oh, yeah,
There we
yeah,
go.
okay. Oh,
Oh.
this looks a little bit small
It was hidden.
and
Sorry.
out of focus. So the talk is called Riding the Web Wave. Okay, and I hope by the end of this talk that you'll figure out what that means. Okay, so, and why I have a picture of the mirrors from the James Webb Space Telescope. Oops, there we go. Riding a wave and which way the wave is going. I don't know. Okay, so the point now, right, so I hope to give you basically an introduction to the James Webb Space Telescope, and in particular to show you the very first image that came from the James Webb Space Telescope. And this was, I must say, as you'll see in the talk, as exciting for me as it was for hopefully for all of you. So I want to help to get some of that excitement across and why we care so much. And in particular then to also introduce you to my field of study, which is called gravitational lensing. And to the team I work with to analyze James Webb Space Telescope data. It's called the Pearls team. That's why we have the telescope here. These are the mirrors. And we pretended it was like a clam, like a clam, and then we put the little pearls inside. Yeah. Okay, and the gift of data I wanted to talk to you about is called the SMACS cluster. So we'll talk about that. So, you know, as much as there is a lot of science that I want to talk to you about that's exciting and new and right on the frontier, another interesting aspect of my group is that I work with a lot of students. I have 6 different undergrads working with me directly, you know, on this work, for which we really publish, you know, at the highest level, and I really enjoy, you know, working with the students. They're listed in yellow here down below. Okay, let's see if we can move along. Okay, so I'm basically a lot of what I enjoy doing is basically studying gravitational lensing. So the idea is that Einstein tells us that mass bends light. Okay, so if you look at a star, say one of these lights in the sky, and you wait, say for example, for a massive object, like what's massive? Yeah, the sun is really close to us, you know, and massive, like 90 million miles. You know, wait for the sun to get quite close to that star, and you'll see that whatever you thought the position was, when the sun gets near it, it'll appear to jump suddenly to a slightly different part of the sky, and then when the sun passes by again, it will go back to where it was. That's not real. You know, you can colloquially call it an optical illusion, but it's because the light is actually bending around that sun. Okay, that's called a lensing effect. So I study lensing effects, and another way to look at it is to think that you take basically a source, and now I'm going to have the sources be all of your faces, and I can see all the faces in this room because I'm not actually totally blind, but I can see your faces, and I can tell that some of you have eyes if you're close to the front, and at the back, I really lose track of how many eyes, you know, and all that. Okay, but consider your faces to be what I call sources, and then when I put this lens in the way of my eye, then suddenly those images of your faces distort into focus. And now I can see that all of you have eyes. Well done. No, okay. Okay. If you don't, it's okay too. But you know. Okay. When I talk about lensing in space, it can seem a bit sort of far out and bizarre. But if you keep that analogy in mind, it will really help. So here's what we do. Then we have basically. See if I can get this to work. I didn't really want that. Yeah, there we go. So what lensing works here is we have a source. You can imagine, again, all of your lovely faces, and then a lens, which would be like an eyeglass lens here, and then the eyes are the observers. So what I do in space is I like to look for sources that look really distorted from what they should look like. Okay, as a result of my viewing them through a lens. Okay. But in space, we don't have eyeglasses just floating around in distant space, okay? But we do have other objects that act like eyeglasses, okay? And they're objects that are very massive, but really dark, actually made out of dark matter, one of the most mysterious substances in the universe, which is also makes it a really interesting topic of study. But if I would have, say, a dark matter glasses instead of actual glasses, then what it might look like to you is just the frame with no glass. You say, oh, she's trying to be quite pretentious. She's got frames with no lenses in them, or something. But it would actually be a dark matter lens in that case, just kind of just a colloquial analogy, okay? So the interesting thing is when we look through natural lenses in space, it looks like there's nothing there at all. But then it makes really distorted images of things in the background, and you say indirectly by analogy that you've discovered something interesting, okay? So let me give some examples now instead of just, Oh, there you go. So there's an example of a lens, for example, which is kind of just dark with some bright spots, okay? So here's an example of an actual lens in space, a simulation of one. And what's happening here is all of these bright spots that you see around, that you saw around, were not people's faces, but actual galaxies. Everyone is a separate galaxy, okay? And then it's like I'm taking the lens and I'm just moving it like this across the audience, and I see some of your faces go into focus and then out of focus again, and then in focus and out of focus again as I move the eyeglasses across the audience. That was kind of the analogy there. And I can show it maybe one more time if we're lucky. So here you can see the light from distant objects being distorted. Can you see the lens? I mean, can you see that it looks like a giraffe or an elephant or something? I mean, people are shaking nodding their heads. Well, nodding their heads, yes,
Stay behind those
because it seems like you could see it, because you could see indirectly all of this distorted shapes, and you say it must be there. And yeah, you're right, but we don't actually see it like you don't see what the object looks like. It's just dark. Okay, so here's an example of a very famous lens. Okay, the biggest lenses are called galaxy clusters. We generally find them because they do have some bright spots in them. Each bright spot is a galaxy with 10 billion stars in it. Okay, so that already sounds like it's quite a massive thing. But there's a lot of dark matter sitting right at that same place, okay, that is far more massive than the bright matter that we see. So this is a lens that we're looking at right here. And what we really want to do is find examples in which we see, say, sources of light, say any of you individuals in the audience, that we see double of you. So when I put my glasses on here and I look out, I see only single faces, okay? No identical twins that I can notice, okay? But imagine if I saw, say, 5 of the same person in the audience cloned, okay? Then that would be an example of a kind of lensing effect I'm looking for. And what do I mean there? I mean, so I showed this example here. I keep almost advancing the slide. There we go. This is an example here, which is hard to see maybe at the back, but this is one person, not a very, very tall person with a long body and a separate person with a big arm and a really kind of wide person. No. This is the same person who looks very different in each of these 3 images, but is still the same person. Okay? So this is what I look like. I'm trying to look for examples of a single source that I can see in multiple places across the lens, but maybe looking distorted somehow. Okay, and I call that an arclet family or an image family. Why do I say that? I mean, it's not a family, it's just a single person, but the collection of images is a family because it's all connected. It's all the same face we're looking for. Okay. So, would you like an example, a real example? Okay, let's show you a real example. So here's another really famous galaxy cluster lens. You might think you do see the lens, right? Because we do see all of these bright spots. Oops, okay. Really did something. Okay, but the bright spots there again are only the tips of the iceberg. All of the dark matter is contained underneath it, but is completely invisible to our eyes. We can detect all of that mass, even the dark matter though, indirectly by the lensing effect I'm talking about. And a really powerful constraint on this dark matter is to find these examples of images for which we see double, triple, quadruple, quintuple. What's after that? Sextuple, yeah. So this is an example of, for example, the sextet arcs. 6 separate images of the same background object. This one is called System 112, which is really, I know, lacks imagination, but and it consists of you see kind of image there. It's contained right here, but there's no way you could see that, so I just zoomed up to make these inset images bigger for you. And this one has like a little piece, looks almost like a little piece of rice or something, and a much more extended little bit there, right? And if you imagine just rotating that sort of counterclockwise, that's it, and then you get this same one here. Anyone see that? Yeah, good. And then if you go back up here and you rotate it like 180 degrees, then you get this one here. You see that piece of rice and the other one. There's one even right in the middle, and this one here is just stretched like taffy. Okay, like that gentleman in the fun house. Okay, but this is an example of in this case, two separate galaxies, 1 and 12, which are imaged into 6 different places across the galaxy cluster. This doesn't happen normally, just as when you get your glasses, you don't normally see 6 different images. If you saw double, you'd take that eyeglasses back to the optician straight away. Okay. And you make them redo it. But in real life, we have the equivalent of lenses, but we don't have opticians and engineers grinding the lens and polishing the lens. It's just natural, right? So it's got all the lumps and bobs and pieces of glass stuck to it all over the natural lens. So you end up seeing double, triple, quadruple, or in this case sextuple image things. And then what you can ask is, this is very powerful, right? I mean, if I'm just looking at faces there in the back, I can't quite tell. Everyone looks pretty much in focus. I think it was a really good optician. I can give you advice at the end. No, just kidding. Good optician there for where to go if your glasses need fixing. But so I think it's really good. But if there are any slight improvements, I can't really tell at this level. It's pretty hard to do. But of course, if I did see 2 of all of you, it'd be pretty obvious there's a significant problem with microscription. Okay, so that means that if you can see these exaggerated effects, then you can get really powerful kind of constraints on what is that prescription. How did it go wrong? Okay, so this is what we look for, are examples of image families like this one, and then we ask, what is the prescription of this gigantic lens that is the equivalent of an eyeglass lens that distorts the images in the background in such a way that you get 6 different images of something. And once we can learn what that prescription is, then that translates directly to the mass and the distribution of the mass and matter in this lens, and that helps to give us insights as to what dark matter is. Okay, so let's get on to the James Webb Science and what we've learned to the test here. So I don't know if you remember, around about in July, for those of you coming to these meetings, you've probably heard about the James Webb Space Telescope. Yes? Woo! Okay. Okay. So it was actually July 12th, in which the first data were released to the public. And, because I'm an astronomer, I didn't get any advance notice, okay, just like you all. But, the first data to be released was released to everyone freely, to the whole public. So everyone could take a look. We all got access to the same data, which is a really nice move that NASA decided to make. But we knew it would be on Tuesday, July 12th. But then on the Friday, we heard a rumor, oh, well, maybe the White House wants to do something on Monday. What do you mean, the White House wants to do something? And so then on Monday they said, President Biden wants to give us the first image on Monday night instead of Tuesday morning. Like, okay. And it will be some galaxy field. Okay, nice. There are 100 billion galaxies, so that's good for someone, I'm happy, So we all kind of gathered around, I think it was about 5 p.m. or something on Monday, July 11th, waiting for this Zoom, that's the wrong one, waiting for this Zoom meeting to start. And I think it was like at least 45 minutes later, an hour later, something like that. And I see heads nodding of other students of astronomy, and I think there was this nice sort of tweet made that astronomers all around the world are nodding their head like a metronome in unison to the elevator music, And then I remembered this dear picture of this empty room, and then this inset of this very this very nice looking lady who was just sitting there like this with her arms crossed for the entire time in live, just had to sit there live with her picture on, you know. We later found out she was meant to be the translator, the sign language translator, but you know she had nothing to say for for 45 minutes. She'd sit there and smile. At least we could turn our video off, you know. But then finally, President Biden comes on and says, "I'm sorry, I was late." And I go, "What am I going to say?" You know, sure you're busy. So there's plenty of trips to the Middle East, you know. And then he and some other advisors got on, and then they showed us the first image, and well, you know, it kind of looked like what you guys are seeing from the back. I mean, this is really what we saw. For those of you who remember on TV, there's this image at the very back. It was quite far away from Biden, and the rest of it quite far away from us viewers at home. They didn't even, you know, give us a nice close-up of the image. But of course, we were taking screenshots of that little bit already, putting them on our iPod and zooming in and trying to do science. And I must say, here's a kind of small zoomed-in version of what we saw that very Monday night, with, you know, my own handwriting written on this iPad image in red here. Lo and behold, I mean, without even having to have much imagination, what do you see but distorted images that look, for all the world, like they are images that are lensed by a large lens that's right in this way. And it just popped right out of the screen at the low resolution high resolution but low resolution because we took it from a screenshot from a distance from Biden's PR. And I just thought, you know, gosh, this is what I was trained to do. And a tear came out of my eye, and I didn't think there would be such a shock because I've been working on the James Webb Space Telescope since the year 2005 in Ireland, where I was first recruited to work on what's called the MIRI instrument in European Consortium, and then from there I got recruited to the University of Arizona, where I've been also working on the James Webb Space Telescope. So if anyone knew what to be prepared for, it was myself, and I was really surprised. So I called a former undergrad at the U of A, who's now a grad student in California, and where I was, and I said, you know, we got to do something about this, you know, analyze this thing. And he said, okay, when? I said, what do you think my answer was? Now. And he said, okay, and my husband said, sure, bring anyone over. So we brought people over, and okay, are you ready?
Yes.
Look at that. Look at that image. I mean, you could just see how that would thrill me, huh? Okay, so this is unbelievably beautiful image with a lot of lensing evidence, a lot of examples of these image families right here. It was a gift, it was a complete surprise. I should say that I guess it was around about 10 years ago now, in 2013, when I set up a branch of researchers called the Pearls team. You heard about Pearls, there I showed you the logo. And we built the team to be able to analyze these data quickly and efficiently, and also get a lot of information out of it. And we'd been sort of planning for, 9 years or so when these data first came out, and then we were expecting our own data in another few weeks. So after 9 years, we were ready to go. We were standing behind the stage, peeking around the curtain and seeing like the orchestra, like the orchestra warming up in the orchestra pit and everything, and we're ready, our makeup's on and our costumes are on, we're waiting for the orchestra to start playing, and then we jump on and then we start typing, or whatever astronomers do, Sorry, yeah, that's why the documentaries are sometimes boring, because it's like, oh, we're typing, But then it was, so we were just waiting for that spark, basically, to get ourselves going. We had built up a team that spanned 4 different continents around the globe. We were just waiting for that spark to get this intercontinental lensing machine sort of running, basically. And we thought it would be our data, which would come in a few weeks' time. But then it's as if we're standing behind the curtain watching for the orchestra to warm up, but they don't warm up. It's as if this time, unlike all the other times when you've been to a concert, this time they just sit down and immediately they start playing. They start playing. You have to run up really, really fast and then start typing. And this is really what happened, is we didn't expect this gift. We didn't expect this extra beautiful images from the James Webb Space Telescope to arrive, just like that. So we found ourselves, my student Massimo and I found ourselves in California, which happened to be the western edge of this big intercontinental machine. And it was around about 6 o'clock at night or something like that when we first got these poor data, and then we got better data on Tuesday morning, which is this one you're seeing here. And then on Monday night, we realized it was our job then to do what we could to start identifying these examples of image families and then send that on to the next person, because people in Europe, in the Middle East, they were all sleeping, but they'd wake up soon, and then at least we'd do our part. So we'd make sure that the project never slept. I didn't even ask my colleagues, hey, you want to do this thing so that the project, project never sleeps and we keep handing it around the world, isn't that cool? Didn't even say that. It just kind of was obvious that's what we'd all do. And then on the East Coast, right, it was heading towards bedtime, 9 p.m., 10 p.m., they'd be, probably thinking more about working the next day. So we did our job. We identified a lot of these images, and you can just see some of the beauty here if I can show you. Oh, I moved it wrong. So these here are stars, okay? And if you ever want to see a star, right, they always have these like nativity scene diffraction spikes coming out of them. That's just because stars are almost like point sources, and when they hit the telescope, okay, they have these diffraction effects with the telescope optics that give you these diffraction spikes. So stars always look like this through a telescope. And in fact, if you, this is really hard to find, right? And in fact, it's like a tiny button. I even have small hands, and it's like really hard. Okay, there we go. And so it's very interesting because each telescope has its own signature of a diffraction spike. So if you're an astronomer, then you can just be shown a star, or you should test an astronomer. Just show them a star and say, which telescope did this come from? And they should be able to answer you. They should be able to answer you. This is the first time we got to really see the James Webb one in real time through everything. But if you want to amaze and impress your friends at a cocktail party, you can show, right, that you can connect the diffraction spike with the actual observatory. So those are always stars. Pardon? Oh, sorry, yeah. So those are always the stars. But I don't really care about stars. They're kind of like the bugs on the windshield, because I study the distant universe. So to me, it's like taking a picture of the grand mountain vista, spreading across the valley, and you've got to take it through the window because it's raining a lot or something, and you see the bugs in your picture through the windshield. It's like that. They're very close to you, these stars, but it's a 2D photograph, right? So you can't escape that part. Okay. So we want to look past the stars, and then we see all of these little white blobs too, whitish blobs. I can never get that right. There we go. Little white blobs. Here's these little white blobs. Those are all the tips of the iceberg. Those tell you really that's where probably the lens is, and then all of the matter that does these distortion, this distorting of images and these doubling and tripling of images, okay, is sitting underneath all of those white dots. Okay, and that is where all the power is and all the mass is to do the lensing. Okay, that's pretty good. Okay, let's move forward here. Okay, so in case you're wondering, okay, looks all right, I guess. Yeah, pretty or whatever. But then I always really love to show this image here, which is the before and after image. This one I think was put out by the European Space Agency. And I think nothing really shows sort of the raw, awesome power of the James Webb Telescope than showing you the before image on this side. You can guess on the left. I'm not going to try to point to it. Who knows what will happen? Okay. And the after image on the right. Okay. Just, it's really as if someone forgot to turn on the lights on the left or something like that, because the image on the right has so much more information about it, and we're really enjoying going through it. So at this point, we've decided that we're going sort of back and forth around the world for about a day and a half now, when we realized, hey, we can actually do this thing. Like we have this machine running, and all of us are so excited about it that we're just going to write up the first paper and just write up that paper on showing examples of all of these image families and showing what kind of how we're able to determine the prescription of the lens that distorts those images. So we started to do that here, and finding these image sets, these arclet families, as they're called, really, really gives you a powerful constraint on that. So I show you now different regions of this image I just showed you before. There's the big diffraction spike with a star and everything. And all these little yellow dots, which are basically an eye chart for anyone, even in the first row, I think, because of the focus. But it's just to show you that there's really a huge amount of lensing evidence in these images. And one can almost say that we went from sort of guessing at one or two of them in the past, or in some cases, which were really well studied, we would have a few dozen. But now we have, in just the shortest little images of the James Webb Space Telescope, we have a kind of an embarrassment of riches. We have so much evidence here that we are really able to get a really good handle on the prescriptions of these lenses, which will help us a lot to study the dark matter. So at this point, Massimo and I and others were able to identify 14 individual image families, and we did this calculation saying, you know, we have 14 different ways in which we're seeing double or triple or quadruple images. And you can imagine you can see double image with the glass arranged in a few different ways, right? But you also have to see a triply imaged thing, and then that narrows where the glass needs to be in the prescription. And then you have 14 examples of seeing double, basically, which in the end gives you a very narrow range of prescriptions. You could be really, really sure that you've got the right prescription, basically, by the end of that exercise. Okay. So for us, we came up with this result here. It kind of surprised all of us. Like I said, I think it wasn't until about a day and a half that we realized we could even write a paper. And then after 3.5 days, we submitted a paper, which turned out to be one of the first 2 papers in the world submitted using any James Webb Space Telescope data. And this is the result that we got. We were able to identify the lens, which is the prescription right here. And you can see it doesn't look like a circle like glasses generally do, but looks a bit more like a peanut, like a circus peanut or something, where the peak part of the lens is given by the white contour. And we also see some really interesting deep space objects as well, which we remark on. I'm going to try this again. Get to it. Okay, there we go. Okay, one of them here I've shown the instant here. I don't know if you can tell, but it's this long, stretchy arc, which is probably a galaxy that's more or less round, but has been stretched by the effect of this hidden lens. But the sensitivity and depth is so good with the James Webb Space Telescope that we see things that we've never seen before in space. And this is one example of those completely new object, which I don't know if anyone can see this at all, but you see a whole bunch of little dots surrounding this galaxy too. At first we thought, oh, maybe those were like mini galaxies like falling onto it or something like that. But it turns out that they're probably newly forming globular clusters. What does that mean? Those are just big collections of stars like bees orbiting a beehive that we have surrounding the Milky Way as well, all around it, in a kind of halo surrounding the Milky Way. And they're the oldest stars in the Milky Way, basically. So it's very interesting to study the history of the buildup of a galaxy, and we might be asking if we're learning something about what the Milky Way itself may have looked at when it was first being formed as well. So then finally, in doing this exercise and learning the prescription of this lens, we were able to find out, indeed confirm, that the dark matter, the part that you don't see, outweighs the bright matter by a considerable amount, and the total weight of this lens, if you put it on a scale, would be about 60 trillion times the mass of the sun. Okay, so that pretty much sums up the talk. I guess I wanted to talk about a little bit what I do, which is that dark matter in space, any massive object really will bend the light around that object. Okay, and it'll not only bend it, but in some cases it can also make the object look like it's 2 images or 3 images or 4 or 6 images of the same background object. And I use as an analogy a person, just as there's only one of you. If I see double, if I see 2 of you, it's not that there's actually 2 of you, there's still 1 of you, but it's an optical illusion that I see 2 of you. So just the same thing with the galaxy. If we see doubles, there's 1 galaxy and I see 2 images of it. And that information is used to tell us basically what is the prescription of the lens doing that distortion. And that tells us in turn about dark matter. Okay, so I also wanted to share with you this James Webb Space Telescope data, which enables the discovery of a lot of deep space objects, new lenses, and distant objects. And the benefit really is the extremely high resolution, really high depth and sensitivity that we get, and the very red colors. Okay, so that's that pretty much sums up my talk. Look in the future for a lot more results coming out from our Pearls program. Oh, okay, yeah, so I've been informed that I should ask one multiple choice question, so I'm going to introduce that. And I asked this one because first of all, there's no right answer, so grad students, people who will earn PhDs in astronomy any day now, cannot win this one, okay? And here it is. Imagine that a NASA administrator interrupts this talk, walks straight down the aisle, with like a bright blue jacket or whatever they wear, and grabs this microphone away from me and says, anyone who wants to go to the moon, come with me now. What would you do? Yeah? You got a 2. Okay, that's awesome. I really want to know. What would you be? 2. Any 2s? We got some 2s. Okay. Okay, good.
I left my tab open.
The tab is fine. We've got 2s. Yeah, so let me read them. So imagine this NASA administrator says, anyone want to go to the moon, come with me now? You've got 3 different options. One is, well, that sounds great. Let me inquire about, the time commitment, the wages, any free NASA swag, and whether the current, I have a job already, will it be held for me, and what are the benefits? Okay. Number 2, stand up, forget to pay your tab, and just follow that person. Okay, that's your chance. I don't know if they ask twice. Okay, or 3, be sensible, go home, think it over. Maybe it is, the adventure of a lifetime.
Yeah, you get to come back.
Do you get to come back?
Is it a one-way trip?
If you think about it, well, but that's not a question. That's not.
So you're number 1. I'm a number 1.
It's like which type of person are you? Would you go first? Would you jump off the cliff and then ask, or later?
By the time they thought about it, the rest of us are on the moon.
Exactly. But there's no right or wrong answer. But I always love to ask this question myself, because I'm really curious to hear what you all think as well.
What's your answer?
Oh, yeah. I think I would drop the mic and jump over the fence, along with all of you who said 2s as well. But I'm different. I've always known that. Okay. All right. Yeah. Well, good then. Thank you. I wanted to ask if anyone has any questions. I guess I was hoping to be interrupted during the talk, but yeah.
I have a question.
Yeah.
On the galaxy with the globular clusters.
Yeah.
In the image.
I want to show this one actually.
Right. Yeah. So, to my eyes, the globular clusters look kind of circular instead of smeared out in the center of the galaxy is. Is that a trick of the eye, or is that because they're small?
Yeah. Well,
I kind of expected them to be more smeared out.
They're not. They're basically not spatially resolved, so they appear kind of as blobs. I mean, marginally resolved. Yeah. But detectable. Unlike Hubble Space Telescope. Yeah. Anyone, at the back, very far back, on the right, yeah.
Hi.
Hi.
So
If this goes in.
I saw, I think on a previous slide, you had talked about identifying the members of these sets
Yeah.
by eye.
Yeah.
Just by kind of parsing up the image. Has there been an attempt to kind of try some computational methods of being able to, or I guess, is it worthwhile based on the amount of data that we're getting from James Webb to be able to try to use computational
Yeah,
methods?
it's entirely computational, basically.
Okay.
Yeah. But it's not a long enough talk to be able to sort of describe all that. Yeah. But we also have, so what we're saying is our initial guesses, I kind of, they get motivated by looking what seems to be a similar shape by eye, and then we also use other information like the colors, because lensing preserves color. So you'd expect to see the same exact colors across different images, and of course you expect the morphology, to stay roughly similar. And also we can use those colors then to estimate a kind of a distance of a sort, and that distance should be the same because it's the same person. If I'm looking at you, there's only one of you, even though I see images here and here, but that distance should always map back onto exactly where you are in the audience. Yeah. So we use all that information first of all, and then we run what we call a lens model, which is computational software, for which we basically have to start with at least one known, multiple image thing like seeing double to get a basic model going. And then we sort of ask can we add another set? And if we add, say, 2 of them, where would we expect a third image? And make sure that we can vet our choices, which aren't always, our imagination can get away with us. So we do use the computational methods also, to vet all of our crazy ideas. Yeah, that's right. Yes, yeah.
Well, so do your computational models account for having multiple lenses between the source and the observer? How do you deal with?
Mine don't account for compound lensing, but yeah. So the question is, can you take into account massive objects at varying distances toward the source, right? So I'm showing you examples here that look like there's just one single gigantic glob of dark matter between us and the source. But we're looking at more than half the look back time of the entire universe. So there's a lot of other matter there. And if there are multiple really massive globs of dark matter on the long line of sight, then each one of them will bend the light in a different way to reach us. Okay, so I don't take into account those compound effects, no. Yeah, at the back, yes.
Hi, thank you for your talk.
Thank you.
Have there been any images that the James Webb have captured so far that have been particularly disruptive to the way that astronomers think about the universe?
That's a really good question. Really good question because sometimes I struggle, just trying to explain that I don't have any really controversial thing to say. So I would say not really. I think because at least because we're kind of in the discovery era, the era of picking up gold off the floor, as I like to call it, and I think we haven't had those big surprises. I mean, there have been a lot of sort of pseudo surprises, like kind of shocking results, some of them that turn out not to be real. So I don't want to recount those because they're not really holding up. I mean, but I would love to turn it around and ask our students. I do have an example, I think, of one idea I think that really surprised me. But before I get to that, I'd like to, if you don't mind, I'd like to ask the PhD students, do you have an example yourself before I give mine? Anywhere? So a couple of, yeah, here we go. So,
I've never seen them.
pardon?
It's like Jupiter's rings, but I
not
don't
really a
think
surprise.
that's revolutionary, but it's cool.
Yes, we have one contribution. In fact, Jupiter turns out to have rings, which we did know before, but we hadn't seen them directly, So we would kind of teach that, but we couldn't really show an image that properly showed rings around Jupiter, and now we can. So those textbook figures will be redrawn. I mean, not redrawn, but the image will be popped in with a new one. And I was a bit surprised to find so many really red spiral galaxies. So a lot of, we have about 100 billion galaxies in the universe. Never mind this mind-bogglingly large number. But what I think is really exciting is not only the large number, but that we kind of only have essentially 3 or 4 different brands, and that's it. We have what are called elliptical galaxies, which look like American footballs. We have spiral galaxies, like the Milky Way, that you've seen the pictures with the really nice spiral arms and everything. And we have sort of irregular ones, a couple of different irregular ones. That's pretty amazing to me. Wouldn't you expect more diversity or variety? I mean, isn't that, to me, that's always been a bit shocking. Why 2? I mean, wouldn't we have all different types of beautiful shapes and things, and we just don't? But the spirals, it turns out, tend to be blue. Whenever you see them, they're blue. And a blue color, in this case, indicates that there's always new stars forming. And if you get new stars form in big groups of about 100 or more. And in that group is always one really heavyweight star. As if whenever you're born, you have 99 siblings, and one of them is a guaranteed sumo wrestler champion. It's exactly that, They're like, oh, I guess that's me, or something. I mean, not me, but, there's always going to be someone who's actually going to be that, And so that one is the big blue one, and that can outshine all the other 100 of them. Really, literally, because it just shines bright blue, piercingly bright and blue. So we always thought all spiral galaxies just had to look blue, and with James Webb we found spiral galaxies that were red. To me, that could be telling us something very interesting about how this branding happens. But yeah.
I feel like I have a silly question based on the ones that were
This has to be the last
asked, but
question.
I'm not a student, so I'm gonna ask it. The gravitational lensing that I'm used to just seeing, it's just kind of those little swoops, or you see around black holes, just a little. So what causes the replication where you see the same image all the time? Is it the distance you're studying, the dark matter that's lensing it, or what causes that?
Yeah, no, well, it's just basically, so it's a combination of 2 things. It's the geometry, so it means that basically the observer, which maybe will have your face, the observer and the lens, I don't know, I guess this will be the lens, and my eye have to be more or less collinear, so sort of in the same line, just about right there. And then not only that, but the amount of material in the lens has to exceed, has to be really, really high, really, really densely packed dark matter into that lens. Dark matter can be kind of light, or it can be like whipped cream, or it can be really dark, And this is the really heavy, and this is the case where it's really heavy and dense. So you have the combination of those 2 things, then you can get double images or more than 2 images. Yeah, really good question. Okay, I think I'm told that that's all that we have time for right now, but I'm really happy to talk more later.
What's that?
Advance a few slides.
Thank you so much for that great talk, Brenda. It was really nice to hear about all your experiences with the early images. So we are running a little bit short on time. So instead of our normal 20-minute intermission, we'll take a 10-minute intermission. Before we do that, real quick, just a reminder, we have new merch. So go check it out if you're interested. After intermission, we'll come back with our new segment, Astronomy in the News. And after that, we'll be playing our trivia game. And we will pass out the answer sheets, and if any of you need any writing implements, we'll pass that out after Astronomy in the News. So it is now 8:21, so we will see you back here at 8:31.
Do we just keep it streaming, or?
Yeah, but mute the mic.
very, very shortly. So please find your seats. Sorry for the short intermission.
Yeah. Oh, sorry. No. I just put my wallet there. That's okay. While I was doing the answer keys. You can't.
So we have a brand new segment this month that will hopefully be returning for future months. Astronomy in the news. And I will just let you take it away now.
Sure. Thank you, Lily. Okay. Hello, everyone. You can do like 15 seconds. Okay. So, welcome to Astronomy in the News, featuring myself and Dr. Danny. I'm Dr. Jackie. So this is my best friend and colleague. We both received our PhDs in astronomy from the University of Texas at Austin a couple months ago. Welcome. And we recently arrived here at Stewart Observatory as postdoctoral researchers, but where our real expertise lies is as news anchors. We presented this little bit at Astronomy on Tap Austin back in the day, and it was a very popular hit there. So we hope that you get a kick out of it too. You can be on the lookout for updates about the solar system and research on stars and planets from Dr. Danny, and I will be your humble presenter of galaxy science, both near and far. So without further ado, let's get into our first Astronomy in the News story. Okay. The universe's cutest baby pictures. Do you ever wish that you could delete those old embarrassing photos of you from when you were younger, smaller, more impulsive? I bet the universe wishes it could too, but cosmological redshift works the same way as the internet. Anything you put out there is still floating out there somewhere if you know where to look. So rumors of this monstrously bright galaxy, dubbed GNZ11, lying at redshift 11, or less than 400 million years after the Big Bang, have been floating around since the Hubble Space Telescope first captured a single filter image back in 2010. So there's like lots of fake stuff out there. So generally if you want to say that something is real, especially in the regime of 5 pixels, you generally want to get a couple of pictures of it to say that it's real, but this thing is so red that Hubble could only see it in one filter. So this is just kind of like a little rumor, a little joke that we had going on. And then we threw a bunch more of NASA's money at trying to look at it with the Keck telescope and other instruments on Hubble. And so faint detections of this galaxy seem to confirm its nascent existence. But now with the spectacular James Webb Space Telescope, we have the most beautiful, clear image and spectrum of this galaxy now confirmed to be at redshift 10.6 and suspected to be one of the brightest galaxies in existence at these early times. So, pictured on the slide over here on the right, yes, thank you for the applause. It's all me, baby. So this is an RGB image released from the JWST team, or the JWST Advanced Deep Extragalactic Survey. Many of the team members are here tonight, so you can talk to them. And the images are captured using many filters inside JWST's NearCam instrument. And so this is seeing the ultraviolet light from the galaxy's stellar and nebular emission that has been redshifted to infrared wavelengths. So we see it as this very red thing. And in a new paper by first author Sandro Takela in the Astrophysical Journal, astronomers have investigated the features of such a young, tiny, and blue galaxy. So you can see by the fact that it's like 5 pixels and is not really like the beautiful stuff that you're used to seeing from James Webb, that it's super compact. That's not just an illusion, it really is that tiny. So it's about 60 parsecs, which is less than 1,000th the size of the Milky Way disk. So it's kind of basically how your jeans fit from high school. This is your like young, small self. So such a tiny, bright galaxy implies a flurry of activity in its core, and that could be to do with things like an accreting black hole or an extreme burst of star formation, and they basically think it's the second one. But the beauty of this galaxy doesn't stop at a snapshot image. Here is the prism spectrum of this galaxy using JWST's NearSpec instrument. And so this is basically your newest member of the Gifted and Talented program for the young and bright. And the spectrum is published in a different paper by Andy Bunker in the Astrophysical Journal, which shows emission lines coming from various metals. And in astronomy, metal is anything that's not hydrogen. You know, it could be a metal if you want it to be. So such as nitrogen, carbon, neon, magnesium. So these are all like boomingly bright. I mean, generally, a really good spectrum is like this. at Redshift 10 and we're like, oh cool, it's like 3 pixels, it's totally a galaxy. But like, this is unambiguous, this is absolutely beautiful, so I want you to think it's as beautiful as we do. So this is the first time in astronomical history that we can clearly see so many signatures of the gas that's mingling in between the stars, and actually do physics, instead of just like pointing things at the sky, which is basically what high redshift galaxy experts do. So the power of JWST to reveal the underlying mechanisms powering a tiny galaxy that is filled with a total stellar mass about 1 billion times the mass of our sun is only the beginning of the many discoveries JWST will be able to make in its final frontier of space exploration. And then I have this whole thing that I was going to teach you about like the physics of hydrogen, but like who cares? Just real fast. Basically what happens is there's a bunch of hydrogen in the universe and it just like gobbles up light. And over here you get this classical break. I wanted to mention this because I saw this in the YouTube comments. Someone was like, hey, there's something wrong with your spectrum. It like cuts out over here. That's real. Hydrogen's gobbling up all this light. And there's this little like baby bump here. We're not really supposed to see it at really early times. All of this gets like super gobbled up along the line of sight. So this galaxy has done a lot of work for the light to reach the eyes of Webb. So this is just a really spectacular, beautiful, historical spectrum. And so if it doesn't impress you, just like ooh and ah for me. So thank you.
Teach me physics, please.
I will be happy to talk to you about physics at a later time. After some more beer. Okay, here you go.
Wonderful. I think my least favorite part about Webb is that I can no longer make the joke that you do all of your science from 1 pixel.
That's fine.
You get single digits rather than just a digit, so that's a plus. And then I think I realized I shouldn't stand in front of that. The last time we were on a stage doing this together was almost exactly 3 years ago. It was the 3rd Tuesday of February 2020.
Aww.
So really, what a return, what a return. Okay, so to move on to our next story. So my own personal research is pretty isolated from any James Webb science, which actually I'm kind of glad about every now and then. But I figure I should jump in on the party for at least one of the stories. But instead of the very large scale galaxies, start of the universe, all of that stuff, I'm gonna bring it back a little smaller scale to kind of answer a question that really motivates me about astronomy, which is really how did life start? Now you might be wondering, what can Webb tell us about the start of life? Right? You might think like, oh, you're a telescope looking far into distant galaxies and whatnot, but you can actually learn a lot. And we can start from the fact that life, right, is made up of all of these building blocks, right? For us, these are amino acids that make proteins and sugars that fuel our metabolism, but all of those building blocks are themselves made out of smaller organic molecules that are made of hydrogen and oxygen and nitrogen and sulfur. So for life to start, we need those atoms to create organic molecules that can then produce life as we see it. But there are some big outstanding questions of exactly how common those types of molecules are in the galaxy. And really, how does a terrestrial planet like our own, the Earth, manage to get an inventory of that type of material to then produce life? And so what James Webb can do is it can look at the clouds in which stars form. So these are giant, massive, dense clouds of molecular gas, and it can figure out what is inside of them. And so this result from the Ice Age team, led out of Leiden Observatory in the Netherlands, they've used James Webb to look at one of the nearest sites of star formation in our galaxy, Chameleon, which the James Webb NearCam image is shown on the left here. And they took, what?
I said that's really pretty.
Isn't it? I saw that and I was like, wait, that's really cool. And so they can point James Webb at this and take a spectrum, which you can see on the right here, and the details don't matter, but you can see these dips, which are all signatures of specific molecules. And so what they can do is they can figure out what type of ices are in this cloud. And I don't mean like, you don't want to take a Slurpee cup and drink these ices, but the ice form of these organic molecules that are necessary for life to form. And so this is actually the most comprehensive kind of census of these organic ices in a molecular cloud to date, which can only be done with Webb because of its sensitivity and the wavelength range that it can cover. And they found a lot of these molecules. They found simple things like methane and ammonia, but they've even found complex organic molecules that they can see the dip and they can kind of say, oh, this is an organic molecule, but they don't even know exactly what molecule it is. That's how crazy these observations are. We need to advance our theory further to figure out what's going on. So this is great. A lot of these complex organic molecules exist out there where stars are forming. So that means that, well, a star forms, a planet can form around that star, and then should inherit some of these molecules necessary for life from the cloud it was born from. So that's pretty cool, right? That might mean that, okay, life might not be that rare to form, or at least the building blocks of life might not be that rare to form. There's a bit of a caveat. They actually found more than has ever been found before, but still less than they were expecting, which is a bit of a concern. But that's really just saying that the molecules are not all in the form of ice. They're in solid form. So that's not great. That's harder to incorporate into biology. But regardless, this really shows the power that Webb has to kind of unveil what is going on in these extremely hard to study, dense clouds of gas in which stars and planets form, and really help us figure out at least whether the things we need for life to form even exist there in the first place.
Thank you, Dr. Daniel. I'm waiting for the follow-up paper that's called Big Gulp. We spend more time coming up with acronyms than doing real science. As you can see right here, let's sink our fangs into some meaty galaxies. So now that we've gotten the baby pictures out of the way, we're done being embarrassed about really tiny, small galaxies. It's time to present the universe's glow up. Okay, so now she's bigger, she's older, and she's way cooler on Instagram. So this is from a recent press release from Webb, which has highlighted some of the beautiful results from the FANG survey. So that stands for Physics at High Angular Resolution in Nearby Galaxies, which is the least tortured acronym that anyone's ever come up with. So that's actually really good. So FANGS has been sinking its teeth into the nearby universe for several years, using almost every state-of-the-art facility known to astronomers, including the Hubble Space Telescope, the Atacama Large Millimeter Array, the Very Large Telescope, the Overwhelmingly Large Telescope, the really big one, and now the James Webb Space Telescope. So GNZ11 that I showed you before, very cool for nerds, but this will knock your socks off. Even way in the back, you can see how beautiful this is. So distant young galaxies basically are blurry Bigfoot-like photographs. But galaxies in our neighborhood can be mapped with beautiful resolution down to small clouds of stars. And so now we can find our place here, and these are from the NGC catalog. That's what I wanted to say there, so great. Eyes at multiple wavelengths are crucial for dissecting the many features of a galaxy's core, in the middle here, and in the spiral arms, because there's not just stars, there's also the dust in between, and there's gas at many different temperatures. There's hot gas, cool gas, whatever that all means, and it's floating in between the stars, and in the space between the stars, the medium that is interstellar, we call this the interstellar medium, the ISM. And so optical light is no secret to mankind. Even the cavemen were able to see all the dazzling light from the stars. But you don't have infrared eyes, and dust is a really pesky thing. It's annoying on your glasses, it's annoying in telescopes. So the reason for that is that it's obscuring some of these really important details of the ISM. And so the internal structure of a galaxy and the space between those stars contains bubbles of gas that are overlapping, these clouds of thick dust that are coming from newly born stars and recently exploded stars. And this is all invisible at optical wavelengths. And it's been Bigfoot level blurry with previous generation telescopes. This is the first time that you can see these individual lanes. This is really incredible. So you remember the first time that you got glasses and you realized that grass is made of individual blades. It's not just a blur of green. So the Spitzer telescope was basically giving us a blur. We knew the grass was there, but you didn't know it was made of blades. And now you can see these individual clouds. So this is the mid-infrared view from JWST's MIRI instrument. And so you can see the dust and the gas in the nucleus of the galaxy and in those dust lanes in the spiral. And on the right here, you're looking at the starlight from the Hubble Space Telescope. That's like the more diffuse starlight. And then you're seeing these individual dust grains out here. So this is basically from the vibration of a molecule called a polycyclic aromatic hydrocarbon. Not the song from Greece, just a pop. So this level of detail allows researchers to piece together the story of how galaxies evolve internally over time, because there are processes that govern the formation of new stars, and you need to know about the gas to understand that. And then there's this natural birth control that all galaxies eventually go through, and they shut down their star formation basically forever. And so with really high resolution stuff, you can actually see this in kind of local neighborhoods. And those are the kinds of things that will funnel gas to the center and allow you to accrete matter onto a black hole. But then there's also this really energetic feedback process where you can have gas get ejected out of galaxies. And so in many more than 5 pixels, we can finally learn about that. Finally. So we have these heated cavernous gas bubbles. This is kind of the warmer gas. And this is a beautiful complementary insight to the stellar populations, as you saw from Hubble, and then the cold gas, which you need to see at millimeter and radio wavelengths. And so these astronomers can do way more physics than what we can do with our 5 little pixels. So these people are actually doing modeling of the gas and the stars and everything that happens, instead of just being 1 pixel equals blue galaxy. So you can check out the FANGS gallery at this link, which is so tiny. But you can Google FANGS astronomy. Just FANGS with a PH. Will give you this goofy pop artist that's 17 years old. And I was way too old. I was I don't understand who this person is or why his name is FANGS or what any of this music is about. So just put astronomy after that, and then you can find all of these beautifully delicious shapes that you can sink your fangs into. There's 19 galaxies in the gallery, so have at it. Thank you.
Woo!
Okay, sorry to James Webb, but we are done with you for tonight. And now, this is actually probably a better introduction to me as a news anchor. Only maybe Logan here in the audience kind of can guess where this is going. But I have a bit of a healthy obsession, sure, with icy moons in the outer solar system and their subsurface oceans. Did I hear a cheer? I hope so. All of you will be cheering after a few more segments from me. Okay. Choo-choo. Really? During the moons? Oh, the train is for the train's a fan too. Okay, well, I think I can keep going for now. So, I love icy moons and their subsurface oceans. Why? You might be like, huh? Well, 1, that just sounds really cool. But 2, more importantly, these are the places that are arguably most likely to have life in our solar system other than the Earth. And here I'm going to talk about 2. The poster children for these are moons like Europa and Enceladus, which are shooting geysers into space, and obviously they're really cool, but the population of these moons with subsurface oceans is actually just growing and growing and growing. It seems like, they're kind of a dime a dozen these days. But I'm going to talk about 2 relatively new discoveries about subsurface oceans. So first is Saturn's moon Mimas on the left, despite the image that is indeed a moon. And actually, this kind of Death Star dish-esque crater is kind of the key to figuring out what's going on under the surface. So when Cassini flew by this before it yeeted into Saturn, I was the first yeet! Wow, this is a shocker. That's real, a few years dated. But so when Cassini flew by, it noticed that this moon Mimas was rotating a bit oddly, which could be explained by a subsurface ocean. But looking at it, it doesn't look like Europa or Enceladus, which have active geysers and very smooth surfaces. This is heavily cratered. It seems to not be active at all. So they were like, oh, maybe not. It's something else. But a recent study from the Southwest Research Institute modeled this impact basin, the Death Star dish here on the moon, and actually found that the crust, the icy crust of this moon, when that impact occurred, had to have been much thicker than it is today. So the crust has shrunk over time, conspicuously after this impact. And so the idea is that this impact heated the interior to actually melt some of the ice and create a subsurface ocean. And ever since, it has expanded, and this ice crust has thinned, and so we actually have a new emerging ocean world in the outer solar system, despite it not looking at all from the surface like that would be the case. Now, on the other hand, we have Pluto's moon Charon, which is kind of in a different life state, in that it used to have a subsurface ocean, and likely doesn't anymore. So our view of Pluto and Charon used to be a single or a few pixels, until the New Horizons probe flew by and took this beautiful image, which is not so beautiful on this screen. But there are these huge chasms and relatively smooth surface in the southern hemisphere that a recent study has gone back and modeled this to find that those could be explained by not a current active subsurface ocean, but an old one that froze over time. And basically, like if you have a container that you fill with too much water and then freeze and then it explodes, that's basically what happened here. The freezing ocean under the surface of Charon has expanded and created these cracks. So you might be thinking these two are like, they're not super exciting, they're not Europa or Enceladus, right? Like Venus barely looks like it has an ocean, and Charon doesn't even have one anymore. But these, exactly! But these are actually really important because one of the biggest outstanding questions about these subsurface oceans is how long they persist for, right? If life is to form under the surface of one of these moons, the ocean has to be there for a fair bit of time. And so actually getting more of these data points and examples of moons that either used to and no longer have a subsurface ocean, or seem to have relatively recently gained a subsurface ocean, help us to understand how they evolve, how we can create, well, not we, but how these moons can have liquid water under their surface that could potentially host alien squids under them. So yeah, icy moons. Thank you. We did it.
Give it to
Oh, okay.
Who's doing this?
You.
Okay.
Yes.
Cool. Thank you so much for that super comprehensive astronomy videos. We're going to pass out answer sheets while the train goes by. Choo-choo.
Yep. That's pretty good timing.
I think the train has mostly gone by, so I can talk now. So while we are in the process of passing out these answer sheets, I'm going to just quickly run through the rules of SpaceDrafts trivia. So, yes, the answer sheets are being passed out now. The format of this is going to be 3 rounds of this slide, so 6 to 8 questions. It's actually going to be 9 questions each. 3 different topics. One is powers of 10, myths, legends, and constellations, and then just kind of general astronomical knowledge. Feel free to play as individuals or as groups. Importantly, if you are a team of self-identify yourselves. If you are a team of astronomers, please put an asterisk in your name. We're trying to keep this a little bit fair for non-astronomers in terms of prizes. So please identify yourselves if you consider yourself an astronomer. We are playing. Yes. On the topic of honor system, we're going to trust that you all will not use your phones. play this in the spirit of the game. If you don't know the answer, take your best guess. No one's going to be judging you. You also have all of the questions, as you might have noticed, on your answer sheets. But we appreciate it if you could just try to track along with the slides as we go. At the end, we will collect all of your answer sheets and tally them.
Listen up! Listen up! This is important!
Yes, at the end, we will pick up all your answer sheets, tally them, and there will be prizes for the top scores, both astronomer and non-astronomer, and we will also be doing a random draw.
Go to the next slide. It says that.
Okay.
Okay, because without Google, I'm not getting anywhere.
Yes, so take heart. If you feel like you know absolutely none of these answers, you still have a chance to win because we'll be doing a random draw for the winners. Did I miss anything on the last slide of the rules? Oh yes, for anyone who's listening at home on the live stream, feel free to play along, but unfortunately we cannot ship you any prizes, I'm sorry. Anything else? Oh, and we do have the answers at the end, so I suppose we will run through those before we collect all of your answer sheets, just so you guys all know what, whether or not you got what answers you got correct. That is what I'm trying to say.
What is the size of the black hole in the center of our galaxy?
Maybe we don't go through the questions. Maybe we just let them answer them on there.
Yeah.
Like so. Yeah, let's set a timer. 10 minutes.
Okay.
I think that's a good idea.
Well, should we put the questions up on slides for the live stream?
Oh, that's true. Okay, go ahead and just announce you have 5 minutes, 10 minutes, or whatever.
So actually, since we are a little bit short on time, actually we're just going to, since you have the entire trivia sheet in front of you right now, just go ahead and go for it. Fill out the answers as best you can, and in 10 minutes we will be collecting them. So you have 10 minutes to do 27 questions. Go.
Go. Yeah, it's 9 questions. Yeah, go ahead and go through this. Go ahead and run through the slides for the live stream in case. Is everybody on the live stream?
We will be running through the slides for the sake of the live stream, but no need to follow along necessarily.
Actually, that's probably a good slide to leave up for a little while.
See, I never had
That's my question. I can remember that. Yeah, that's true. Kind of requires.
But then there's also the thing.
These are hard. Like two of the rounds being an astronomer doesn't help you. For the first 2 rounds. Here, you guys can read the next one.
Is that the proximal one?
You know what? This is fun. I like doing it this way, where they just have free time to answer. I like that. Okay, that's fine. It is.
We're guessing.
The elephant is really throwing people. Because, you know, I didn't have a spring. I know.
Yeah, I just that's
So we have decided to give you all 15 minutes instead of 10. So you now have 10 minutes left. Yes, we have time travel.
Good job, everybody. I like doing it. I don't like having it. You also didn't have the question.
What's that?
I was wondering if that was yours. Yeah. They were so mad about the order of magnitude rounds. They're hard. They are. Remember, you still win. You're going to get nothing
absolutely not. I mean, it would if I had the time to calculate it, because I could, but it's really fucking hard. I can't do it. I'm more mostly good. What's the general, so wait, what is the distance? during this time.
I'm sure you're right.
I know, she said she had 2 kids to go on. You mean the underground? Yeah, no, I haven't. I would love to. Yeah, because I wasn't with that. Why do you keep cool. Yeah, I would love it. I'm very happy. Can I give you give you short cards? About that, and I okay, then awesome. Yeah, we would love to get that going.
I'll ask her. Why did you write our name? I did that. I'm not even that was my dream.
So there are about 5 minutes left. Is anyone feeling the urgent need for more time than 5 minutes? I'll give time at 5 minutes, and if anyone's not done, just let me know.
This is gonna eventually. Is that like a weird kind of temperature?
I'm trying to face it with all of them. She didn't actually say that.
Do you want the pencils back?
And if anyone gets done early, feel free to bring them up to us early.
Yeah, we're supposed to bring it up. Okay, that's so much. I want to see that. Are we dating already? Yeah. Fantastic.
Actually, no, I hate that rule, but I'm just saying.
Well, you were working Mr. Geyser. Let's ask her. It's all good.
What, pencil?
Pencil. Thank you.
What was yours?
Wild card. Yeah.
Those first two sections.
Yeah, you can chat with them.
You guys need help grading?
How are people doing? Does anyone need more time?
20 seconds.
20 seconds.
20 seconds. Cool.
There was some second and third and fourth guessing.
You know? That's the win. You never know.
So my colleagues are all back there frantically grading. So top. Does everyone else? Are there any answer sheets still out there?
Yes.
Yes.
1 minute. 1 minute. I'll pass it to you.
30 seconds for any outstanding answer sheets, and then I will start going through answers. Turn in your answer sheets now. Any more out there? Are we all good? Do we have all the answer sheets in? Cool. So, while all my colleagues are frantically grading all of your answers back there, I will tell you what the correct answers are. So, round one, powers of 10, or as we try to name it, orders of magnitude. I think powers of 10 is better. So, roughly how many meters in diameter is the sun? The options are a billion, a trillion, a million, or 100,000. The answer is about a billion. And remember that astronomers really like to round things, so we never put a number other than 1 at the beginning. It's just a 1 followed by however many zeros. So, number 2, what is roughly the distance to the nearest star, Proxima Centauri, in centimeters? The options were 10 to the 12, so 1 with 12 zeros after it, 10 to the 18 centimeters, 10 to the 25 centimeters, and 10 to the 35 centimeters. Turns out to be 10 to the 18 centimeters. Number 3, what is the mass of the black hole at the center of our own galaxy, Sagittarius A star, in the units of the average male Asian elephant? And to be honest, I did not write this question. I do not know how massive the average male Asian elephant is. But the options are 10 to the 20, 10 to the 27, 10 to the 33, 10 to the 40. Eventually this will advance. Nope. Okay. Well, okay. 10 to the 40 is the answer. You also probably got the answer.
Wait, is that?
Is it? Did this get offset?
Yeah, the circles that moved.
This got offset.
Woo!
Remember how I didn't write this question?
No, it's deep. Sorry, it's deep.
Okay, so it's 10 to the 40. This answer kind of already got spoiled for you, but the number of stars in the observable universe is closest to the number of humans that have ever lived, which is about 10 to the 11, the number of ants on Earth, which is 10 to the 16, the number of gallons of water in the Earth's oceans, 10 to the 20, or the number of grains of sand on all the Earth's beaches, 10 to the 22. And it is about the number of grains of sand in all the Earth's beaches.
I don't know what happened to the circles.
I'm going to be doing my best to guess where these circles are supposed to be, unless I really can't, and then I'm going to get the answer key.
It's my laptop's fault.
So, what is the mass of the Sun in units of the mass of Pluto? Or in other words, how many Pluto masses make the mass of the Sun? The options are 10 to the 5, 10 to the 8, 10 to the 10, and 10 to the 20.
Let's see. Whatever.
It should have been This is also not advancing. I'm going to guess. Can I have the answer key, actually? I'm going to guess that this one is supposed to be 10 to the 8. Give me 2 seconds to get a computer that actually has these aligned correctly. I'm so sorry.
Who made these slides?
Never SpaceDrafts got massive technical
I know.
Okay, start. What happens?
Every goddamn
Oh my God.
I am so sorry for all the technical difficulties. You're also going to probably have to take my word for what's supposed to be circled. But I swear I do have a computer with this aligned correctly. So, what is the mass of the Sun in units of the mass of Pluto? About 10 to the 8. Okay, how many Jupiters by volume could fit inside the Sun? The options were about 100, about 1,000, about 10,000, 100,000, or a million. I accidentally advanced the slide too much. It's about 1,000. Roughly how many Mars planets, again by volume, could fit inside of Jupiter? The options are, again, the same as before, 100, 1,000, 10,000, 100,000, or a million. This one is 10,000, which just is not going to show. Take my word for it, it's 10,000.
Oh my God! You've skipped 8.
And the, can you go back? We're going to see if advancing from the computer works any better than me with the clicker. So, what is the approximate atmospheric pressure on the surface of Venus? Venus in units of the Earth's atmosphere. In other words, how much more atmospheric pressure is there on Venus than on Earth? The options were 0.1 or 10 to the minus 1. 1, which would be the same as Earth. 10, 100, or 1,000. It was 100. Number 9, compared to the Sun, how many times larger is the radius of, I should have looked up how to pronounce this word.
UY Scooty.
Can you tell I'm an extragalactic astronomer? One of the largest known stars. The options were 10, 100, 1,000, 10,000, and 100,000. The answer to this one was 1,000. And this was the end of round 1. So I hope everyone is feeling at least sort of okay about how they did. To be honest, none of the astronomers really knew the answer to this one. It was hard. So if you got any right, be proud of yourself. So, round 2, myths, legends, and constellations. How are the zodiac constellations determined? A, they are the constellations that ancient people use to guide their lives. B, they're made up. C, they're the most easily recognizable constellations. And D, the orbits of the planets and moon/sun passes through them. It is D. Number 2, how many constellations are officially recognized by the International Astronomical Union? The answer is 88. Number 3, what does the word planet mean in Greek?
It's weird. It's advancing here, but not up there.
Technical difficulties. Anyways, what does the word planet mean in Greek? Turns out to be wandering star. Number 4, the brightest star in the sky, Sirius, and it has a white dwarf companion, Sirius B, and they together collectively have a nickname. What is that? It's a dog star and a pup. Answer A. The Tohono O'odham legend. Which Sonoran desert animal was appointed by the people to study the stars? It's a coyote. Number 6, in Chinese folklore, the moon goddess Chang'e is accompanied by what animal, which is also the inspiration for the name of China's moon rover, was a rabbit.
See the rabbit?
Oh, yeah.
See the outline of the rabbit on the moon? Some of you in the back probably can't. Number 7, the Pleiades, which is also known as the Seven Sisters, it's constellation, or actually star cluster, is known by what familiar name in Japan? Subaru, which I suppose was given away by the logo.
And that's the Subaru telescope. It's not named after the car, it's named after the Pleiades.
We needed pictures on our test.
Also, interestingly, the Subaru logo only has 6 of the 7 stars. I've never understood that. Number 8, in Greek mythology, the constellation Draco represents a dragon. What does it represent in Arabic astronomy? It's hyenas and camels. And finally, number 9, what is thought to be represented in a famous rock art painting at Chaco Culture National Historic Park in New Mexico, which is shown here. It's a supernova.
Yep.
And that was the end of round 2. Again, this was another round where studying astronomy did not actually really help you. So again, if you got any of those correct, be proud of yourself. Finally, round 3, just kind of general astronomical knowledge. Of these solar system objects, which do we observe going through phases on Earth? We see Mercury, Venus, and the Moon going through phases. Number 2, astronomers use the, in my opinion, worst unit in the world, magnitudes, to describe the brightness of objects in the sky. Of the options listed below, which of them corresponds to the brightest object? It's -2. -2 is the brightest object.
Correct. It does not make sense.
It does not make sense. This is why I don't like it.
Yeah, here we are.
Number 3, if we could travel at the speed of light, about how long would it take to get to the nearest star to our sun? It's about 4 years. Number 4 was a matching question. We were given 4 components of the universe, asked to match them to which fraction of the universe they make up, and I'm sorry it was not formatted particularly well in the answer sheets. But dark energy makes up about 70%. Dark matter makes up about 24%. Ordinary matter makes up about 6%. And light is less than 0.1% of the universe. Number 5, when our sun eventually evolves into a red giant star, which is when it dies, how far will it likely expand to? Earth's orbit. What do we call the day of the year when the sun reaches its highest point in the sky? It is the summer solstice. It does not depend on the hemisphere. It's the summer solstice. So Jupiter has aurorae. What wavelengths of light does it emit in? Ultraviolet and X-ray, and we also took either one. You didn't necessarily, I think, need to put both for the answer. Either one was accepted. So any elements that are heavier than hydrogen and helium are made in stars. And as Jackie alluded to earlier, astronomers are incredibly lazy and just call all the rest of them metals. What is the heaviest element that can be produced by fusion in the cores of stars before they die? It's iron. And finally, which of these objects is not a type of dead star? It is a brown dwarf, and
What is dead can never die.
and Rachel is up here cheering because she studies brown dwarfs. Yes. And yep, I think this is it. So we will now announce the winners.
All right, I get the joy of announcing the winners. So, the second place prize for the non-astronomer team, you win this sweet Kepler planet poster puzzle. And I know, it's really cool. And the winner is Space Squids. Come get your prize. And the first place non-astronomer team, you win a $25 Borderlands gift card.
Woo!
Borderlands is great. We love them. And that goes to Kevin Squared.
Nice, Kevin.
Come on, Kevins. Get your border card. Gift card. Okay, and the top scoring astronomer team, you win an item of your choice of SpaceDrafts merch. Or there's an ESA mug you can have too. Galactic Menopause. Wish I didn't relate to that. And your random draw, you also win a selection of SpaceDrafts merchandise. Goes to Jackie. Danny won't help Stacy. I think that means Stacy won. Okay, come on, Stacy. Congratulations, everyone! Woo! Thanks for an excellent show, and we will be back the third Tuesday of March. We'll see you here. Hopefully we will not summon the rain like we always seem to. And we'll see you back here Thursday, Tuesday in March. Follow us on Facebook, Twitter, sign up for our mailing list to get all of our news and information, and see you then. Oh, don't forget to come buy merch.
By the way, I have free beer here if anyone wants. Because they kicked the keg like right before they ended up pouring. So I was like, is that going to go to waste? I was like, if you want it, you can have it. So.